Hi everyone, my name's Alfredo Olmedo. My partners were Michelle Narvaez, David Gonzalez, Vera Ruiz, and Han Lin. Our advisor was Dr. Julio Gonzalez, and our senior design project was a programmable charger for the development of new batteries.
I'd like to start by describing that why is our design important. First of all, charging batteries directly by a voltage source can be very time consuming. Our design speeds up the charging process by maintaining a stable current level. And also, our design facilitates developers to perform tests to find the most efficient charging schedule. To touch on these 2 points in more details, charging batteries directly connecting the power supply and the battery will be time consuming because the voltage from the battery is increasing while it's charging, and then by an Ohm's law, the charging current decreases and thus slowing down the charging speed. Our design adopts a closed loop system to address this problem. In this system, the information of the current is passed back to the initial stage of the system and compared with the reference voltage. Errors between them will determine whether to supply more power or less. In addition to that, by programming the input reference voltage, developers will have the control of that charging current as well.
For this product, the user will be required to select the current they would like their battery to charge at. They will not be able to charge a battery past 12 volts because the transistor will saturate at that point. That same transistor will also heat up at high currents, introducing the need for a heatsink to dissipate the heat. Lastly, the microcontroller will not be able to output more than 3.3 volts for a reference voltage. Some principles in theory that we used from our engineering courses included those from electronics, where we used op amps in our control loop and capacitors to keep that control loop stable. We used an NPN transistor to produce the current that would charge our battery. From control systems, we were able to design our closed feedback loop and also use the transfer function to help troubleshoot our circuit.
Heatsink theory. Due to the amplifying current, the Darlington transistor will increase in thermal energy. The heat dissipated is equal to the product of the collector emitter voltage and the collector current. Power dissipated is equal to the change in temperature over resistance magnitudes between the 2 points, analogous to Ohm's law. This provides a framework to analyze heat flow through the system using a resistance model. Put simply, heat will travel in 2 directions. 1, conduction through the case and convection into the outside air. 2, conduction through the case, mica sheet, copper heatsink, and back into the air. Adding these 2 resistances in parallel and solving for RSA determines the required resistance the heatsink design must meet to dissipate the internal heat generation imposed by the circuit during operation. In the past 2 semesters, we've learned a lot of things to bring us into our final project. For example, having 4 op-amp chips instead of 1 to make troubleshooting the breadboard easier. Noticing that as the resistor standing in for the battery decreased, the control loop would become unstable. We started by using values at 10 kilo ohms and worked our way down to 15 ohms. Also learned that we had to use a low resistance power resistor as our sensor that can dissipate heat and provide voltage input to the buffering op-amp in the control loop, because normal resistors cannot dissipate that much heat. Through the whole process, we used steady state and transient thermal simulation analysis to help us predict max temperature of the transistor and heatsink at different working currents.
Our prototype was able to solve the following problems for us. We were able to charge up to 12 volts at a constant current in simulation by performing a DC sweep. With the breadboard prototype, we also avoided the danger of overcharging the battery by using a resistor instead. We were able to output a desired current set by a certain reference voltage on that breadboard, and this allowed us to be ready to add charging schedules from the microcontroller as well.
For our design iterations, we tested the circuit using capacitors to help reduce the noise and hit the target value more efficiently. We also tested the circuit with a resistor in place of a battery, which helped us to get a head start on the project while waiting for the battery and observe the behavior with lower currents. We then tested the circuit with different batteries to see how efficient the circuit was. And we also replaced the battery using a DC motor to see if we needed to make any changes to the circuit itself or just use other batteries. Some of the key design features include the power supply that can handle more than 0.5 amps, so we can test the circuit with higher currents such as 1 amp and 2 amps. We also have a microcontroller that provides the reference voltage and a programmable charging schedule. We also have our PCB board, which is this control loop system that will allow the current to remain at a constant value. And we also designed a heatsink for the transistor to avoid overheating.
Some recommended improvements for next iterations are to come up with an overcharge protection to avoid overcharging that can potentially damage the battery. Also to design a more user-friendly program that can work with lithium-ion batteries. And to come up with a performance data graphic user interface for some sort of data collection where the program can read off the current value every couple of seconds at different voltages applied to see if the current remains the same while the battery is charging. And it's important in the future to come up with some sort of reverse polarity detection or protection to ensure that the device is not damaged if the power supply polarity is reversed. And some significant challenges that were overcome was that before implementing the battery, we used resistors for testing purposes, so we had to figure out the limitations of the resistance for our system to work. But once it worked, we replaced the resistors with a DC motor and it worked as well. But once we tried to replace it with the battery, we started having problems. And we were able to figure out that that's because the load resistance of the battery was giving a huge gain at a very high frequency, which makes the system unstable. In order to fix this problem, we placed a capacitor in parallel with a 100K ohm resistor and the circuit worked. That's because with this capacitor placed, the battery now has a very low internal resistance and it reduces the gain at a high frequency, making the system stable. We'd also like to give a special thanks to our advisor, Professor Gonzalez, and everyone else who made this project possible.